Okay, this is a quick video to emphasize pretty much the most important concept when we're discussing projectile motion, and that has to do with the idea of vector components. So let me just show you what I mean here. Imagine we had some object that was launched, say a ball. It would have some initial velocity, and as a result of its motion, initially it's going to travel up through the air and come back down to the ground. And so as a result, it'll have a certain amount of displacement, we'll call that delta dx, and it'll have a certain amount of displacement horizontally, delta dy. Now, the important factors here is that what's so critical is this initial velocity, because this initial velocity actually has two components to it. It has an x component, right? It has a certain amount of velocity that's trying to push the object horizontally, and it has a y component, and there's a certain amount of the velocity that's trying to lift the object up. Alright, so that's all well and good, but what's interesting is how those vector components change over time. So what I'd like to do is show you a little animation that I think really sums up the key idea here. So let's move there. Okay, so take a quick look at this animation that I just pulled off of the web from the physics classroom. And what we see here is a cannonball that's being launched off a cliff, and it initially only has a horizontal velocity vector to it, but that it's falling towards the ground here. And what I think is the coolest about this is it shows you the breakdown of the two vectors. We notice that from the beginning, the cannonball only has a horizontal component, and over time the vertical component starts off very small and then it gets larger and larger, which is what we would expect because it's speeding up, it's accelerating as it's moving down, and so therefore going faster and faster. Okay, so just to point out what I meant here, as I said, the initial velocity here is just x, and then at the beginning we see there's only a small y velocity, but then over time it gets bigger, and it gets bigger, and it gets bigger, and it gets bigger, okay? Which is what's giving us this parabolic shape throughout the course of the motion. Now the thing that I can't emphasize enough is to notice that the x component of the initial motion does not change. At no point in this entire motion does the x velocity change its size. It's always the same size throughout the entire motion, which is exactly why these seem to be fairly equally spaced over the course of the motion, because in the x direction there are no forces. There's nothing speeding this object up or slowing it down, and as a result, horizontally speaking, if it had an initial horizontal velocity, it will simply continue to have that same horizontal velocity for all time, except that it obviously hits the ground, and that's what stops the motion. But other than that, the horizontal velocity is constant and doesn't change. However, the vertical velocity does change. It goes from 0 at the beginning all the way down to whatever its new value is at the very end. Okay, so when I go back to this key idea, I really want to emphasize that horizontal motion is independent of vertical motion. This key idea is critical to understanding vector components. It means that if I took any particular vector and I broke it into its x component and its y component, let's call this viy and this is vix, that as the object moves through its entire motion, this vix will not change. It'll be constant that entire time, whereas the viy will decrease as gravity slows it down and then increase again in the negative direction. So viy is a changing value, but vix is not a changing value. It is constant simply because there are no forces that are acting horizontally. The only force that's acting on this object is the force of gravity, and it only acts in the vertical direction and therefore only affects the y component of the velocity. Now, it is technically possible that there could be a bit of air resistance along the horizontal path, but it is so negligible or small that in general in physics we can pretty much ignore it unless the distance was so large. Let's say you were traveling across a continent, then in that case then air resistance becomes important. But for small motions like throwing a football or serving a volleyball or hitting a baseball, any of those typical projectile motion that only happens over a small distance, we can essentially neglect air resistance and simply assume that horizontal motion is constant throughout.